Pointer is simply a memory address, and a pointer variable is a variable that is specifically declared to hold a pointer or a memory address as its value. At this point, we can say that a variable can be an ordinary variable. This is the variable that we've been discussing so far. We call it an ordinary variable. Examples to this are those variables that we have declared with atomic data types such as character. Okay, say if you declare CH as type character, then we consider CH as an ordinary variable of type character. And say you declare X as an integer variable. So again, we consider X as an ordinary variable that holds ordinary values such as integer 1, 2, or negative 12, any integer type. And the second one is the pointer variable. So what is the difference between an ordinary variable and a pointer variable? An ordinary variable such as this one, ch type character, x type integer, say y of type float, and z of type double, these variables hold ordinary values. Say, for example, ch can be assigned the symbol m. So that is how you assign a character value or constant to variable ch. And say you can assign the value negative 13 to integer variable x. And say to y you assign an ordinary floating point value, say 3.157. And for z, maybe this would be 561.314987. Okay? While for pointer variable, this is a variable whose value is a memory address. It's not an ordinary value, but its value is a memory address. So say, for example, if we look at the memory representation of these variables, say we declare x to be a pointer variable, you put the prefix symbol asterisk in here. So this time, x is no longer an ordinary integer variable. X now becomes a pointer variable. What would tell you that a variable is a pointer variable? This symbol that is a prefix to variable x. Okay, so whenever you see this symbol, it means that x is a pointer variable. So again, earlier we declare x as an ordinary integer variable, so it can hold any ordinary integer value. But this time, we declare x to be a pointer variable. What x holds now is a memory address. So say this is the RAM, and this memory location is allocated for variable x, and say that the memory address of this memory location is 95, and the value we assign to x here is negative 13. So now that x is a pointer, it doesn't hold anymore an integer value but a memory address such as this 95 here. There are two pointer operators that we can use when dealing with pointers. The first one is this symbol, which is an ampersand. And when you encounter this operator, you can simply read it as memory address of the variable that follows. So when you declare x as an ordinary integer, and then you declare, say, p as a pointer of type integer, then p is assigned a memory address, say for example, the address of x. So this is how you write it, ampersand x. So this is read as memory address of x. So say X is located at memory address 95 and this has a value negative 13, then this expression has a value 95. Okay, so if you are referring to X only, the value is negative 13. But if you are referring to ampersand X, it means memory address of X, and that refers to 95. Okay, so take note of the difference between these two expressions. X, an ordinary integer, has an ordinary value of negative 13, while this expression ampersand X has a value 95. Okay, so ampersand X refers to this, the memory address of the memory location where X is allocated, and this one is the value stored inside the memory location. The second operator is asterisk, this symbol here. And when you read it, you simply read it as the value located at the address that follows. So being an operator, it has an operand, and the operand is a memory address, like this one that we have declared here, which is P. So when you have assigned P to ampersand X, what is now the value of P? It would be the memory address of X, which is 95. So the value of P is 95, the memory address of X, since you assign this expression to P. And make sure that whenever you assign a memory address of a variable to a certain variable, make sure that that variable P is declared as a pointer by putting this symbol as a prefix upon declaration of the variable. Take a look at this example we have here. In this code, we declared two ordinary variables, A and B, and the data type is type integer for A and B, while X and Y are pointer variables. How do you know that these are pointer variables? Because of the symbol they are prefixed with. So the asterisk, remember from our earlier discussion, the asterisk is read as value at memory address. So this signifies that X and Y are pointer variables. So again, A and B are ordinary variables. They are assigned ordinary integer values, while X and Y are pointer variables and they are assigned memory addresses as their values. Now look at the main memory or RAM representation for this variable. Say this location here is the memory location for variable A, and this is for B, and this is for X, and this one is for Y. If we assign these values 12 for A and 27 for B, then what we have here in the RAM, for A, we have here the value 12, and for B, we have here the value 27. Now, remember that this value 12 is not the same as this value here, because these values here are memory addresses. When we reference variable A this way, we are referring to the value of A, which is 12. While when we say ampersand A, this is equal to 170, because 170 is the memory address of A. So again, recall from our earlier discussion that this symbol ampersand means memory address. So you read this as memory address of A, and so it gives you the memory address of variable A, which is 170. While when you just simply say A, you are referring to the value stored inside that location, which in this case is 12. Now, since in these two lines here in the program, we assign ampersand A to X and ampersand B to Y, that would simply mean that the value stored in the memory location allocated for X would be the memory address of A. And what is the memory address of A? It is 170, right? So since ampersand A, or the memory address of variable A, is in this case 170, and then by this expression we have here, or this assignment statement we have here in our program, assigning ampersand A to X, so the value of X is 170. So what we have here in the memory location of X is 170, which is the memory address of A. Now, is 170 an ordinary integer? No, it's not. 170 is not an ordinary integer value. It is a memory address. While this 12 here and 27 here for B are ordinary values. So take note of the difference between ordinary values such as 12 and 27 and memory addresses such as 170 and 172. Now, why is it that in the memory location of variable y, we have this value 172? Why is that? Because we have here in the program the assignment statement assigning the memory address of B to Y, and therefore the memory address of B, as you can see here in the representation, is 172, and that's why we have this value in here for variable Y. So when this line here is executed, it's like if this is the memory location for A and the value of A is 12, as we assign it here in the declaration. When this is executed, you have here X as a pointer pointing on the location of 12. So you can represent that statement this way. That is the effect of this statement. And so for the second line, say this is the memory location of B and the value of B here is 27. And when this is executed, it's like Y, a pointer, is pointing on the location of the variable B. So that when we reach this line code, printf, and we are to output or display the value of, for the first conversion specification, you have to output A. So that is the conversion specification for A. So what is the decimal integer value of A? It's 12. So that's why we have here 12 in the output window. And the second one is for B. And what is B? It is 27. So this is 27. The third output would be for, how do you read this expression? It is the value stored at X. What is the value stored at this address? The value of X is 170, right? The value of X, as you can see here in the memory representation, is 170. And this value 170 for X is actually the memory address of A, okay? That's the effect of this statement here. So when we say asterisk X, with this operator asterisk, we mean the value at, what is X? 170. So the value at memory address 170, if you look at the RAM, it is 12, which is the value of A. So asterisk X means the value pointed by X, because X is a pointer, and what it's pointing at is the location of A, and inside A, this location, we have 12. So the output here would be 12. And for the last one, asterisk Y, what is asterisk Y? It is read as the value at memory address. What is the value of Y? The value of Y in the RAM representation is 172. So we would say asterisk Y is equal to asterisk 172, which is equal to what? The value at address 172 is, this is 172, it is 27. So asterisk y is 27. Or you read it as the value pointed by y. What is the value pointed by y from this diagram? It is 27. So the output here is 27. So again, the value of y is 172, which is the memory address of the memory location for B. And in here, the value of X is the memory address of A, which is 170. So X is equal to 170, and that is the memory address of this location, which holds the value 12. So the output here is 27 for Y. So again, first take note, ampersand A is the memory address of variable A, which in the example above is 170. And when we set X to this value, ampersand A, it makes X to be equal to 170 because 170 is the memory address of A, referring to this one. And since X and Y are pointer variables, their values are memory addresses like 170 and 172 respectively. Therefore, asterisk X means the value at memory address of X. So that's how you read this expression. Or the value at memory address 170 is 12. And also, for asterisk Y, it means the value at memory address of Y, or the value at memory address 172 is 27. In this second example, we declare here two ordinary variables, same as the first example, A and B. So A is an ordinary integer variable assigned with the value 12, and B is set to 27. So A and B again are ordinary variables holding ordinary integer values 12 and 27 respectively. Now this X and Y here are pointer variables, and specifically we call this single indirection pointers. Single indirection pointers. And these new variables we declared here, P and Q, are called multiple indirection pointer. Now, how do you distinguish between single indirection pointer and multiple indirection pointer? As you can see here, these variables X and Y are single indirection pointers because they are prefixed with only one asterisk, while these two in here, P and Q, are prefixed with two asterisks. Specifically, these two variables P and Q are called double indirection pointers because they have two asterisks as their prefix. Now later, we will discuss the difference between single indirection pointer and multiple indirection pointer. Now recall the first example we discussed earlier. The pointer variables we have there in the program, which are X and Y, are single indirection pointers. If we represent these variables A, B, X, Y, P, and Q in this figure, say this is the location for A and its value is 12. So we have 12 here, and another ordinary variable B with value 27, and X and Y here are single indirection pointers. P and Q are multiple indirection pointers. A and B are again ordinary variables. So since in this statement we set to X the memory address of A, so recall again that ampersand is read as memory address of. So this is read as memory address of A. that is assigned to X. What is the memory address of A in the memory representation? It is 170. Therefore, X is equal to 170. That's why we have here, in the memory location for X, the value stored inside is 170, which is the memory address of variable A. And on the second line, we assign the memory address of B. This time, it's the memory address of B that we assign to Y. Now, since Y is a single indirection pointer, we can assign the memory address of an ordinary variable. So, if the memory address of the memory location for B is 172, so the value of Y stored in the memory is 172. As you can see here, in the location for Y, the value stored inside is 172. So these two lines would tell us that the only value that you can assign to single indirection pointers are memory addresses of ordinary variables. In the next two lines, we assign the memory address of X. Take note, X is a single indirection pointer, and the memory address of that single indirection pointer, which is X, we assign that to P. Now, this is only valid if P is a multiple indirection pointer, or specifically double indirection, and which is, of course, true. As you can see in our variable declaration, we declare P and Q to be double indirection pointers. And so, since they are double indirection pointers, what you can assign to these variables are the memory addresses of single indirection pointers. So again, single indirection pointers can hold memory addresses of ordinary variables, and double indirection pointers can hold memory addresses of single indirection pointers. So it's like single indirection pointer points to ordinary variables like A, like X is pointing on A, and on this statement, we say P gets address of X. P is pointing now on X. So again, this is ordinary variable A. X, which is single indirection pointer, points to an ordinary variable, and P, being a multiple indirection pointer or double indirection pointer, it can only point to a single indirection pointer. So if the memory address of ordinary variable A is, from the given figure, is 170, then the value stored here in the location for X is 170. Why? Since we assigned the memory address of A to X on this line here in the program. And on this line, we assign the address of X to P. Therefore, the memory address of X, which is, in our example, it is 174, that is also the value stored in here. So take note that P and X are pointers, and their values are memory addresses since they are pointers. While the value of A is 12, which is an ordinary integer value. That's how these three variables are related. For ordinary variable B, say this is the location for B with value 27, and by this statement in our program, this statement here, assigning the address of B to Y, then our Y now is, being a single indirection pointer, it points to B due to this statement, and so the value in here is the memory address of B, which is, in our example, it is 172. So this is also 172. And for this line, we assign the memory address of Y to Q. And take note, Q is a double indirection pointer. So since it is double indirection pointer, it can only point to a single indirection pointer. And this is Q. What is then the value inside? It is the memory address of y, which in our example is 176. So since this is memory address 176 and q is pointing on y, then the value in here is 176. So this is how the three variables are related. B, an ordinary variable, is pointed by a single indirection pointer, and q points to y. This is double indirection pointer. So what type of pointer can point to an ordinary variable? It is the single indirection pointer. The double indirection pointer, you cannot set it to point to an ordinary variable because that would violate the principle behind using pointers. So what you can assign only to point to ordinary variables are single indirection pointers, those variables prefixed with a single asterisk in the variable declaration, okay, as you can see here. And what can point to a single indirection pointer? What type of pointer that can point to a single indirection pointer? It's the double indirection pointer like Q or P. And again, it's not valid to make a double indirection pointer point directly to an ordinary variable in this case. So this is not valid. Okay, so you avoid this action, making double indirection pointer to point to an ordinary variable. So that should be the series. Single indirection pointer points to ordinary variable, and double indirection pointer points to single indirection pointer. And you could also declare triple indirection pointers. All of these double indirection, triple indirection pointers and above are called multiple indirection pointers. So what is the output of the program? Now that x points to a, holding a value 12, and p points to x, so this is 170, this is therefore 170, and x is 174, so this is 174 also. And we have here b with value 27, and the single indirection pointer pointing to b is y. And so since b is located at memory address 172, this is also 172, the value of y. And q, the double indirection pointer pointing at y, has a value 176 since y is located at memory address 176. Now with this, what is the output of our last statement? We have here 1, 2, 3, 4, 5, 6 values to display. The first conversion specification, that is for the first variable here in the list. And that's easy. A is just 12, so that's the output there. 12, the first one. And the second one is for B. B is 27, so that's why we have here 27. And the third one is for asterisk x. So again, remember, asterisk means value stored at x. So x in this case is 170 since it is pointing on the location of A, located at address 170. So if we're going to evaluate this expression, this would be asterisk 170. So asterisk means value stored at 170. Look at the RAM and what's stored inside the memory address 170. It is 12, the value of A. So the output here is 12. Next, it is asterisk y. Asterisk y, that is simply the value stored at, what is the value of y? The value of y is 172, which is the memory address of B since y is pointing on B. So this is asterisk 172. And what is the value stored at 172 in the RAM? It is 27. That's why the output here is 27. And for the next one, asterisk asterisk p, we have here double asterisk since p is a double indirection pointer. And asterisk is a unary operator. It is evaluated from right going left. Asterisk is a right associative operator and therefore it is evaluated from right going left. Unlike the MDAS operators, they are evaluated from left to right. They are called left associative operators. But for asterisk, again, it is right to left. So take note of that. And so the one at the right side is evaluated first. So this expression is equivalent to having this parenthesis, asterisk, and we enclose in parentheses the next asterisk and then the P. Okay, so because you are going to evaluate the rightmost unary operator first. After that, you move to the left. So the asterisk P here is simply the value stored at P. And what is the value of P? It is 174, the memory address of X, because it is pointing on X. So this is bring down asterisk, and this is simply asterisk 174. What is the value stored at memory address 174? It is 170. So this is now bring down the first asterisk, and then the value of this expression is 170. Asterisk 170 means the value stored at this memory address. So look at 170, it is 12. What we have there is 12. So this expression is equal to 12. That's why the output here is 12. Now, the same is true for the last expression, asterisk, asterisk, Q. Q is a double indirection pointer pointing on Y. And so to evaluate this, we say asterisk, and then you could enclose this with parentheses to put emphasis on the order of the operator's precedence. So this is asterisk 176. So what is the value now at 176? Looking at the RAM representation, it is 172. Therefore, this is 172, and then you bring down the other asterisk. This is now read as the value stored at 172. So you take a look at 172. What you have in there is the value 27. Okay, so that's why the output here is 27.